Okay, so I think it's 3 o'clock, so I'm going to start if that's okay. My name is Dima. I use the shell a lot, and let's see, does this work? Sorry, is that too small? Yes, too small. Okay, it's okay. I can work around that. Give me 1 second. Let's do. How about? Okay, let's make that work. Call 50. All right, how about that? Is that better? Great. Okay. Okay. So I use shell a lot. I wrote 2 tools to help me in my own work day to day, and I've been finding them very useful. And so I've been trying to proselytize a little bit because I think the general enough that other people would find them useful as well. So there's plenty of documentation on these things. I could stand up here and read you the manuals, but I don't think any of you want that. So I'm going to instead of having slides, I'm going to do some live demos so you can actually see the thing work in real time. And so feel free to ask me questions as I go, and we'll see how this goes. 2 tools. One is called Feedgnuplot. It reads data from a pipe and makes plots. And the other tool is called vnlog, and it's essentially a wrapper around awk, so it is able to manipulate textual data in very useful ways, as you will see. Everything is free software. Everything is in Debian unstable. The plotting tool is much more mature, so it's currently available in much more places. But with time, they were both kind of propagate. Right. So these are. Let me just say a few more things. So these are written in the spirit of Unix, in that they're both toolkits, so they both have a large number of very simple tools that you can string together with pipes. So it is very generic, and they're both meant to function with the rest of the normal Unix tools, like all the greps and the sorts and all that sort of thing. So since they're general, they're not a perfect choice for any one application, but they're a good choice for a whole wide range of them. And the whole idea is that it's standard, so you can very quickly generate pipelines that solve your problem and move on. Okay, so the overarching philosophy is to create as little new knowledge as possible. So as you will see, most of these things are actually wrappers around existing tools that already exist. And if you know how to use the existing tools, you pretty much already know how to use this stuff, because they don't just work like the tools they wrap, they are those tools. Okay, so the plotting tool has much more clear applicability, so I would like to talk about it first. Okay, so let's visualize standard input. Let me actually do that. Perfect. Okay, so before we can, do that. Okay. So before we can plot anything, so you can all see that, right? Good. So let's make some data to plot. So I will just run sequence 10, and it will just generate numbers 1 through 10. And there they are, right? So this is a normal tool. We all have it on our machines. And in its most basic form, I can just take that, and I can send it to the plotter with nothing else. And if I do that, I get this. And so it's scaling things in a funny way, but it doesn't matter. So there you go. You have points, 1, 2, 3, 4, 5, and so on. So we didn't ask to do anything specific, so we got kind of the default set of settings. We can do fancier things. If we want lines and points, I can ask for that. And if I do that, there you go. So you got lines and points. So very simple. So I should say that most of the interactions, most of the options to this tool actually feed directly to Gnuplot without any interpretation, which means that if you know how to use Gnuplot, you already know how to use this tool. And if you don't, you get to learn 2 tools for the price of 1. But with very, very common things like lines and points, I do have specific options, like dash lines does the right thing. So as a demo of that, if I want something fancier, like lines, points, some particular point size and some particular point type or something, I can just do this. My tool does not know what the string does; it just passes it directly down. So, which means that it's as powerful as the underlying tool is. So if I do this, I get circles, I get lines, yeah. Okay, so Right, so it might look cryptic, but it isn't, because that is just what Feedgnuplot does. Furthermore, if this tool is insufficient for whatever reason, or if you need to, or if you are trying to debug your command, you can actually pass --dump, and it'll generate the Feedgnuplot script that runs inside. So if you do that, here's your script. So this is a normal Feedgnuplot script. You can just save it to a file if you want, and just give it to Feedgnuplot, and it'll work. Or you can add to it. You can do whatever you like. Okay, but since this reads data coming in from a pipe, that means that all the normal pipe things work. So for instance, if your data is not coming in all at once, but if you're reading a pipe where you're getting real-time telemetry from something, then you can plot the data as it goes. So you can get a real-time plot that shows you, something interesting. So I can make up an example where I have a little Perl script that just generates some numbers, and sleeps after every number. So it generates some data, doesn't matter where it is at 1 hertz, sends it to the plotter, and I pass --streams to tell it to, re-update itself as it goes. And I give it some particular styling, doesn't matter. But if I run this, what you get is, hold on, if this worked, there we go. So this is updating at 1 hertz, and there you go. So that little Perl script generates a little sinusoids. This is made up, obviously, but as you can see, you can imagine plenty of applicability for this. All right. So that's made up, but let's change it and make it into something that's less made up and more obviously useful. So this is a laptop. It has a bunch of temperature sensors in it. They actually measure an actual thing. So let's read those and let's plot those in real time and see if we can make something interesting. So if I read this magic file, it'll give me the current temperature readings. So if I do that, this is what the file produced. So it says temperatures : then each number is some particular temperature probe. In order to plot this, I need to get rid of this part, but the rest is just numbers. I can plot them. So I can do exactly what you expect to do. I can have a little while loop. In the loop, I read this thing. I get rid of the temperatures : I print it. I sleep, and then I pipe it to this guy. So what you would expect that I would do. So if you do this, you get this. So the x-axis is time. It's updating at 1 hertz. I can ask for different update rates, but it's 1 hertz by default. The machine isn't doing anything interesting right now, but I will make it do something interesting in a minute. But you can see that it does something. So you can see that a whole bunch of sensors are sitting here at -128. So those sensors clearly don't physically exist. So the driver knows that they might exist, but so it's outputting bogus numbers. So let's get rid of them so I can make it a little nicer. So I can read this. I can pipe it to awk to print only the columns that I know have data. Again, I can do a sleep. We can send it to the plotter, and we can actually do some nicer things. We can label the axes. We can put a title in. You can do as much. You can get as fancy as you like. So when you do that, you get. Sorry, this thing is misbehaving. I'm not exactly sure why. Hold on. Okay, this is my Emacs. It's not happy. Hold on. There we go. Okay, fine. So same thing as before, but we have labels. We have time. So Feedgnuplot, so you can zoom in. You can do all the normal Feedgnuplot things. Fine. So okay, yeah. So that data is boring, but I can prove to you that there we go. I can prove to you that it's actually doing an actual useful thing by spinning a core. So if I go over here and I just make bash, I just make this thing do an infinite loop. So now one of my cores is sitting there evaluating true over and over and over again. You would expect that something is going to get warm. There we go. So that works. The data is not made up. Clearly, the tool is doing something interesting. This also tells us that the core that the sensor that the CPU is attached, the temperature sensor that sits in the CPU is sensor 0. So I didn't know that before, but now I know this. So we learned something. So I can turn it off, and after a minute, you're going to see it go back down. So you know that's a useful thing. All right. So yeah. So when I did this earlier, it was actually probe 7. So something changed in the last hour. Someone should look into that. So okay. So you can imagine what you might actually want to do is you might have a long-running process that logs temperatures or something. And that process might want to log the data to a file, so you might have days or hours or days or years of this data if you wanted to. And you might be able to want to plot it in various ways. So what I can do is I can, in my shell, I can do this. Let's make it bigger. Yeah. Sorry, the screen is not, the resolution is different from what I was going to be. So, right, so you have the same loop that reads temperatures, but instead of plotting it, I just send it to a log file. So this thing is going in the background, so you can imagine this thing has been running for months, just accumulating data in some way. And, I can go back here and I can plot it, so as before. So there we go, so this is the data I just gathered. Not interesting anymore, but that's how it is. But since it's just normal stuff, I can give the file to tail-f, which instead of reading the whole thing, it's actually going to read just the last little bit, and as more data is written into the file, it's going to plot it. And it can do that in real time. So this way I can sort of get the best of both worlds, where I have, I'm logging data to a file, and I can also get the real-time telemetry from it. So if I do this, and there's something with the Emacs, there we go. So it's the same thing. So, so I can get both logging and visualization together. With just normal tools, I didn't make this up. And that's pretty nice. All right. So, yeah, so this is pretty useful. This took no effort. We just did the normal thing. So one question that comes up is like, why are you doing any of this data analysis in the shell? Because you could use MATLAB or Python or Excel or something. And the reason is that we already live in the shell, and it's super general. You can hook it up to all sorts of this other stuff that, Excel wasn't designed to talk to, right? And that is the big win here. And you can get as fancy as you want. So you can do remote telemetry, because you can SSH to a remote server and read their, web server logs and make statistics with awk or something. And just, with SSH, the pipe just transfers over, and you can remotely monitor this stuff. And that's pretty useful. Okay, so the tool, so this was just the bare minimum of the tool. It can do a million more things. You can manipulate various sizes of things, the colors of things, the symbols. You can make plots in 3 dimensions. You can make files that plot themselves, which is pretty useful, because you can just send someone a data file, and they just execute it and just plots it. It plots itself. You can make PDF. Yeah, it's fancy. All right, so this is useful and so on, but if you just think about the temperature example a little more, there were some things that would be really nice if it did. So for one thing, the log file there is just data. So if I've been logging it for a month and I go back and look at it, I don't know what this data means anymore. What does each column mean? Is it Celsius? Is it Fahrenheit? What's my logging rate? Like right now I know that it's 1 hertz, but I'm going to forget this. So just comments in general would be nice. It would be very nice to have some sort of field labels. Timestamps would be good. And this is a good segue into the other tool, the set of tools, and how they resolve this sort of these sorts of things. Let's not go into that. Let's do this instead. Okay, so right. So what you have seen is what I used to do for years before I wrote this toolkit, which is you just generate data, use awk to munge the input in some way, and then do whatever you want with it. So vnlog, which is this other toolkit, lets you do that in a much nicer way. So first off, what is this? So So vnlog is a data format. It is 90% what just works in awk anyway. So it's an ASCII table. The records are separated by new line and the field is separated by white space, which is what awk does by default. It can have comments, so any line that starts with a hash mark is a comment. And the first normal comment labels your field. So, a trivial example is something like this. So this thing is a comment. The first hash comment is field label. So this file has a time column and a temperature column. Here's some numbers, here's some more comments, and some more numbers. Okay. So that's it. So since hash is a comment, it means that you can give this to any tool that knows about this. So numpy.load text, you can just give these files and they will just work. You can load these into Excel or whatever it is you like. You're not tied into a particular workflow, which is useful. This text, you can write these to printf if you wanted to. So the toolkit provides some nicer ways to do it, but you don't have to use them if you don't want to. And again, as before, everything is pretty close to being a wrapper to something else. You don't have to learn anything else. There's very little extra, the learning curve is very, very friendly. So I can say more stuff about it, but I don't need to. So the tool has some libraries to help read and write these things, and some command line tools to actually do various manipulations. And the tools are much more interesting than the libraries, so I'd like to do some demos with them. All right, so let's make our temperature situation better. So let's do the logging in the same way as before, but before we actually read the the device, let's actually write our comment. So say echo comment. Here's my temperature things, and then the rest is the same, and I write it to this file. So let me do that in my shell. Okay, so that is going. So we're now sitting there. It's gathering this data. It's doing the useful thing. So the extra line is still a comment, so I can feed this file to the exact same plotting command as before. Like this is not modified at all, and I can run it, and it will just work. So same thing as before. I didn't have to change anything. But since it has this extra little header, I can do more things. So if I tell the plotter that this is a vnlog by adding this, it will be able to make intelligent labels. So if you look at this, this is the legend. So before the legend says 0, 1, 2, 3 because it was telling me what column the data was in, but now it tells me what the data actually is, right? So here the data is just temperatures, but you can have a million different things, and useful labels are very important. And this just worked. I didn't have to, I didn't have to tell the plotter, column 0 is this, column 1 is that. It got that information from the log file, which was nice. I can do much fancier things. So for example, let's say I want to, so this is a made up example. Let's say I want to pull out just the column that was for the temperature that was sitting in my CPU. Let's say I wanted it in Fahrenheit for some reason, and let's say I want to rename it. So you can use the filtering tool for that. I'll tell you a little more detail about that later, but in its most basic form, it's able to select particular rows or particular columns. You can do these manipulations. You can rename things. So -p selects columns. So here I select a column called CPU temp F, and I set it equal to this expression. This tool is actually a wrapper around awk. So this expression goes into awk directly, and the only change that it makes is that it knows the temperature 0 is column, 0, whatever it is, and it'll convert that to $0. And that's it. So this thing is as powerful as awk is. If you want to know what it supports, the answer is man awk, and it'll tell you. And if I do this, there you go. So you get the one column, and here are the numbers. And note that the format of the output is exactly the same. The format is still a valid vnlog, so you can actually chain these things together, right? Because this thing still has the comment that tells you what the fields are. They're different now, and it still has the data, and so you can feed that to whatever the next thing is. And for example, I can take my file that I have now, I can pull out that one guy, convert it to Fahrenheit, I can plot it. So this is 100% the same plotting command, right? It just, we'll see a different data at its input. And there you go. So it's not doing anything interesting, but now you just have one thing, that's the name, and you can see that it's, 100 degrees, which is what it is in Fahrenheit. Okay, we're good? Great. Okay, so I want to do another test, another demo of that's completely different. It's going to show a few more of the analysis tools, and then hopefully I will finish quickly, and then I can take questions. Let's see. Okay, so let's talk about April tags. So I'm a roboticist, so we have a lot of, in the day-to-day there are a lot of, you talk to a lot of robots that move around, they produce telemetry, you might have a vision system that tries to look at them and find out where they are in some way. So one common set of tools, and these aren't mine, but I'm going to use them for the demo. One common set of tools is called April tags, which are similar to QR codes. So here is so here's an example set of April tags. This image is from the website of the lab that developed it. So they're similar to QR codes. The difference is that they encode a lot less information than a QR code, but they do it much more robustly. So this can be messed up. There can be a whole bunch of noise, but you can still see the tag and figure out which tag it is, and compute exactly the coordinates of the corners in the image. And these things are great. I have nothing to do with them. I didn't write them, but they're useful. So what we can use my tools for is to try to figure out just how robust these things are to noise. Because if you're going to use these things, that's actually pretty important. Like how dark can you make the image and still have these work? So let's do that. So they have a little demo application. So this is the April tag detector. I can ask it to produce vnlogs. I'm giving it an image. So this is the image that I showed you guys. And I can run it, and bam, there it is. So it produces a log file, with a whole bunch of stuff. So I should say that in my day-to-day now, I use these log files for everything. I routinely make log files with hundreds of columns, and I can't read them, but the tools can. They can pull out whatever they need to. But this isn't that bad, relatively speaking. So you get the path to the image. So here, there was just the one image. You get how many detections. So there were 7 here, and these are the various metrics. The hamming and the margin are the various metrics the detector gives you. The ID is which tag it is, and these are the various pixel coordinates of it. Right, I don't need to say in that. Okay, so one kind of problem with this is that as a human, this is not very easy to read because the columns aren't aligned. So I can feed that to this tool, and that will keep the data the same, but just add some white spaces and align it. So if I do that, you get something like this. So same data, but I can sort of see what's what now, which is nice. Okay. Yeah, it's useful. Okay, so another thing I can't do as a human is that I can't tell if this is right. So there's some numbers with coordinates. They sort of look fine. I can manually open the image and sort of poke around in the coordinates and sort of see if it's correct. But it would be nice to just be able to visualize the whole thing at once. And then you can see if you'll be able to directly see if it's doing something incorrect. So I can do that in 2 steps. First, I pull out just the data I want to visualize. In this case, it's the ID and the coordinates and the center coordinates of each tag. There's a reason I'm doing it in this order. I'll get it. Ask me later if you want to find out. It's all in the documentation. But trust me, this is what you want. So when you do that, these are the results. Again, you can see some x coordinates, some ID, and some y coordinates. And as I'm sure you can imagine, I think you can see where this is going. And then I can take this thing I just did. I can pipe it through the plotter. Same tool as before. I give it dash image, which will overlay the data it's plotting on top of the image, so I can clearly see that it did the thing that I wanted it to do. and a couple of things that don't matter, but the result is this. So this is the image. These circles are the thing we plotted, so they're kind of hard to see, so I can actually turn this thing off. So these are the circles that are the center of the detection. The colors are which tag it is. So for example, yellow is tag number 10. So this looks kind of funny, like why are there two of these? And if we put the image back, you can see that these things actually are mounted on this cube, and there actually are two of the same tag on the side. So this actually did the right thing. And here you can actually see how good APRO tags actually are. Like it saw that and was able to detect it and identify it properly and put it in the right place. So APRO tags are good. Yeah, and another thing that these sets of tools give you is that if you didn't have them, if you were doing this manually, you would maybe manually check 2 of the detections. But here I checked them all, right? So if some of them were wrong, if I was doing this without the tooling, I might miss them. But I didn't miss anything here. I know that they were all right, well, right, ish. We'll get into that in a second. And I know that none of them were completely, off in the clouds. Okay, so I don't want to get too deep into the details. It doesn't matter. So, all right, so let's see how robust this thing is to noise. So in real life, if I was doing this for real, I would have gathered a whole bunch of images into different lighting conditions. And then I could run the detector for each one and look at the intensity of the images to look at how dark the thing is, and then kind of look at those things together. So here I'm going to fake it. I will write a little loop to use image magic to actually change the brightness and the contrast of the thing, and just add some noise. So I will write my thing, right? And so here's the images made, and I can go through them. So I just made these, right? So some of them were clearly way too bright, some of them are too dark. So if I was looking at this as a human, like this looks like a pretty terrible image. So if it failed in this, I wouldn't hold it against it, but we can check. So I have a separate image for each one of these guys, and the actual contrast number is in the file name. So like this guy has a contrast of -30. And again, since I'm faking it, what I can do is I can write a little bit of sed, that's what I wrote, to actually look at the file name to pull out the actual contrast. So when you run this little thing, you get this vnlog, which just tells you the path and the contrast number. So in real life, I would have a little thing to actually look at the image, look at how bright it is. But for this talk, this is fine. Okay, so I have that, and let's also actually run the APRO tag detector over all the images. All my images, I'm going to do this. And the tools don't dictate any particular workflow. I could make a little loop and have a separate file of detections for each image, but it's a choice. The choice I made here is to just make one file with everything in it. And I can do this, and it's going to crunch for a while, and there you go. So this is long, right? So this tells me about detections in my whole data set. And fortunately, I have tools, so as a human, I don't actually need to read this, because that would take a lot of my time. And yeah, okay, so I have 2 logs. One has detections, one has contrast numbers. I want to be able to compare them together in some way, so I am going to join them. GNU Core Utils has a join tool. How many of you have actually used it? Nobody. Awesome. Anyone? 1 person. Like 3 people. Sweet. Once. Yeah. So before I did this, I knew the tool existed, but I have never once actually used it, just because it's kind of a pain. You have to match the columns. Yeah. So now I use it all the time because I have this guy, VNL join. So it's a wrapper around join. So 90%, if you want to learn how to use this tool, 90% of what you need to know will come from the join man page, which is not mine, thankfully. And as with all these kind of wrapper tools, the main difference is that any place where you would give it a column number, you give it a name. So instead of saying, take this file, join column 3 and column 7, you would say, here, join on time, or whatever you're doing. Another nice advantage of that is that if your log files change, and then time used to be in column 3 and now it's in column 5, my command can stay the same. And that actually turns out to be very important, because it's very easy to mess up. So anyway, so I'm going to call join. I'm going to join on the path, which that's the thing that tells me where my image is. Here are my 2 log files, and then I will send it to this file. So if I do this, bam. So the path, detection, and if I go to the very end, I have one more column and contrast. So that data came from the other file. So now I have one log file with all my data in it. So now I can visualize stuff together. Yeah, and this is an inner join for all your database people. The join tool can do outer ones and various other things. Read the man page. It's surprisingly powerful, actually. Yeah, and as before, the output is also a valid vnlog, so you can chain it and send it to other tools and all that wonderful stuff. Yeah, so just because I can, let's run it through a sorter. So same thing, it works the same as the other one, except I'm sorting on contrast, not on $2 or whatever it is. And there you go. So I'm not actually using this for anything, but this is just to show that you can do this. And I do this all the time now, which I did not anticipate doing before. All right, so let's see how well the detector worked. So let's look at the contrast. So here I'm doing a filter, so I'm going to pull out just 2 columns, the contrast and the detection counts. So the plus means throw out all rows that don't have any data in that column. Yeah, and send it to the plotter so we can see it. So if I do that, I get this. So let's see. There we go. So the X is the contrast, and the Y is the detection count. So it looks like here, for contrast values that were either way too low or way too high, you see only 6 tags, but for the other ones, you see 7. So it means that it actually mostly worked, across the whole range. Even in the darkest image, it didn't find 0 or 1 tags. It found almost all of them, which is kind of shocking. So this already gives us an indication of how good this thing is. But we have a lot more data, so we can do more. We can look at more things. So I'm not going to get into the details. So first of all, let's just confirm that it really did work in the darkest image, because that image looked awful. So let's take our join file. Let's pull out the detection coordinates, but let's also, so this pulls out particular columns, but let's also pull out only rows for which this is true. So, I'm looking at the darkest one, which is -40. So this guy, will just take my file and give me only data about the darkest image, and then just send it to the plotter. So this is just a sanity check. So there we go. So indeed, we have our terrible image, and it actually looks like it kind of works. And you can see that the missing detection was this horrible one in the corner, the one that looked a little ridiculous that I was able to find in the first place. So if I zoom in on this guy, like with the original image, it was able to find the detection here as well. So that's the difference between the 6 and the 7. And that looks awful. I'm okay with it not being able to find that. Okay, so apparently it worked. So one potential question is that how consistent are the hits? So these are all really the same image. So if this thing worked perfectly, when it gives you the coordinate of the tag, they should all be exactly the same, right? So if there's noise, they won't be, but we can visualize how bad it is. And I can do it this way. So this is pretty much the same guy as before, except here I don't care about which tag it is, I just care about where it is. And I'm taking all the images together. So if I zoom in on an arbitrary one, so there's the spread, for this particular tag. So it's not perfect, but this isn't terrible. So let's see, man, this resolution is awful. So if I want to measure like the distance from, let's say from here to here, that is 0.2 pixels. That's pretty good. Yeah, and here I can turn off the image if I want. Yeah, so you can actually see the colors tell you which tag it is. So one thing you might discover if you did this, you might see an outlier. You might see that there's one detection that's way off to the side for some reason. And then the question is, well, which detection is that? And here they're all crosses, so you can't really tell. But I can plot things with I can plot things with labels. So if I do that, and it helps if I do this. Okay, sorry. Yeah, this is a screen thing. We don't need to worry about that. So if I do that, this is the same plot as before, only except for x's, it will print the ID of the thing. So if it just so happen to have an outlier, you know, this will just tell me which one it is, and then I can, I know what to do. So, right, so I'm almost done. So okay, so we saw that across a pretty wide range of contrasts, the detection counts are pretty good. We saw that the spread looks reasonable, and you know we can do more analysis to actually draw histograms and look at the extra distributions if we want. I think that's fine for this. So one last thing we can do is that if we look at the actual output of the detector, we can see that it actually gives you some error metrics. Like it gives you Hamming distance and the margin. So we can look at we can ask it how well it thinks it's doing by looking at its own metrics. And we can do that by doing this. So I'm pulling out the contrast and the margin, and then I'm just plotting it all together. And you get this. So, this looks at all of the images and all of the tags. So the x-axis is the margin, so how well the detector thinks it did. And you can actually clearly see that there's kind of a parabolic trend. So in the images that weren't too dark or too light, you can see that it thinks it did a little bit better. And that's it. So just a set of demos. As before, this thing's more powerful and there's more things you can do, but you guys feel free to ask me stuff or look at the documentation, man pages, and various demos that are online, and that's it. Any questions?
Let me get you the mic if you have questions.
Will you share your org mode file on
Say it again?
Will you share your org mode file on GitHub?
I can. Where should I? Maybe in the repo. Yeah. Let me do that. I'll put it in the repo. Yeah.
Do you have any examples where you're doing like top 10 in a column or in counts or any averages, sums, something like that?
I don't have any examples, but you would do it exactly how you would do it. So like if you didn't have vnlog, how would you do it? So if you wanted top 10, you would do a sort and then you would do a head. So that's what you would do, right? If you wanted averages, so what I would do, without this, I would write a little bit of awk to actually do running sum and at the end divide. So that's what you would do. So I should say that the VNL filter tool, all the modes you've seen using it so far are, I've only showed you how to pick out rows and columns, but since internally it generates awk and just runs it, that's what it actually is doing, you can just run it in that mode. If you say --eval, then you quite literally just give it a bit of awk, where the only difference is that instead of say $5, you say time, or whatever it is, right? So that was how I would do it. I would write an awk script, but inside the VNO filter, so I don't have to remember which column's which.
Could you display the top of the document that shows where the repo is?
Yes,
Thank you.
That is a great idea. Right there. Yep.
Can you do histograms in?
Oh yeah. Every day. And I mean, this is trivial to do here. I would just do a stupid one for you. Sequence 100 pipe feed. Sorry, I can't see both sides at once. Dash histogram. So you tell which column is the histogram. So column 0, that's all we have, and say bin width 1. So what do we expect? Yeah. Boom. Wait, here we go. And actually, while we're on the subject, let's make it slightly more interesting. Let's say I want to let's say print $1 times $1. I'm not totally sure what I expect, but let's find out. Probably, I don't know, 5? Sorry. What did I do? Oh, yeah. Wrong quote. There we go. Okay, so this is not interesting. Lots of counts. I need a bigger bin width. Hold on. 50. Ah. Okay. I don't know. Why not? Anything else?
Well, thank you very much.
Somebody got.
Oh, just kidding.
So I'm kind of a plant. I've heard that this is also in Debian.
Oh yeah. Oh yeah. Yeah. So both Feedgnuplot has been in Debian for a few years, so it's unstable. The vnlog is in SID. We are going to do a new release in a few months probably, and it will be in that one. Yes. 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 Okay.
Yeah, thank you very much.
Thank you.
The last talk.